Beat, beat, drums, blow, bugles, blow. Through the windows, through doors, burst like a ruthless force into the solemn church and scatter the congregation. Into the school where the scholar is studying, leave not the bridegroom quiet, no happiness must he have now with his bride. Nor the peaceful farmer any peace, ploughing his field or gathering his grain. So fierce you whir and pound, you drums, so shrill you bugles blow. Beat, beat, drums, blow, bugles blow, over the traffic of cities, over the rumble of wheels in the streets. Are beds prepared for sleepers at night in the houses? No sleepers must sleep in those beds. No bargainers bargains by day, no brokers or speculators. Would they continue? Would the talkers be talking? Would the singer attempt to sing? Would the lawyer rise in the court to state his case before the judge? Then rattle quicker, heavier drums, you bugles wilder blow. Beat, beat, drums, blow, bugles, blow. Make no parley, stop for no expostulation. Mind not the timid, mind not the weeper or prayer. Mind not the old man beseeching the young man. Let not the child's voice be heard, nor the mother's entreaties. Make even the trestles to shake the dead where they lie awaiting the hearses. So strong you thump, O terrible drums, so loud you bugles blow.
Lebenstage. So schnell, so schnell, so schnell, ein rauschend Wasser schießt so eilen unseres Lebenstage, so eilen unseres Lebenstage, so schnell, so schnell, so schnell ein rauschend Wasser schießt so eilen unseres Lebenstage, unseres Lebenstage, unseres Lebenstage. Die Zeit vergeht, die Stunden eilen, wie sich die Tropfen plötzlich teilen, wenn alles in den Abgrund schießt. Die Zeit vergeht, die Stunden eilen, wie sich die Tropfen plötzlich teilen, wenn alles in den Abgrund schießt. So schnell ein rauschend Wasser schießt. So schnell ein rauschend Wasser schießt. So unseres Lebenstage, unseres Lebenstage, unseres Lebenstage. So schnell, so schnell, so schnell, ein rauschend Wasser schießt, so eilen unseres Lebenstage, so eilen unseres Lebenstage, so schnell, so schnell, so schnell ein rauschend Wasser schießt so
Henry David Thoreau urged each person to mark to the beat of their own drummer. But what if you couldn't tell the sound of your drum from the sound of somebody else's drum? So the question, can you hear the shape of a drum, was asked by the mathematician Mark Katz in an article he wrote in 1966. And before I tell you the answer, I want to explain the question a little bit. And in order to explain the question, I'm going to first start with a simpler question, and that's, can you hear the length of a string? So what happens when you pluck a string? Well, here I've got a mathematical simulation of what happens when a string is plucked about a third of the way down. And you can see it's quite a complicated motion that ensues. And mathematically, and indeed also musically, it's convenient to represent this motion as a superposition or a sum of much simpler motions. In music, these would be the pure tones that the string produces. In mathematics, this is known as an eigenmode decomposition. So each of these modes oscillates at a fixed frequency, and you get the motion at the top by adding together each of these motions. That will give you the motion at the top. And you can see that the motion on the left is the slowest. That's the lowest frequency. That would be known as the fundamental. And the other two motions are getting successively quicker. Those are the higher harmonics or the overtones. So let me put some numbers on that. If I said this was an A string, say A2 on a piano, so that shows you where the key is on a piano, that would correspond to an oscillation of 110 hertz. So that means it goes up and down 110 times every second. So this video is very slowed down. If the fundamental is at 110 hertz, then the first harmonic is the first overtone, so the second harmonic is exactly twice that. And so the second frequency there is going at 2 times the first, so that's 220 hertz. And doubling the frequency means you go up an octave. So the second harmonic here corresponds to the key A3 on the piano. And then to get the next harmonic, I add another multiple of the fundamental. So that ends up being 3 times the frequency of the fundamental. So that would go up to 330 hertz, and going up by a factor of 3/2 corresponds to going up a major fifth. So that takes me to E4. And one of the reasons that stringed instruments sound so melodic is that these intervals are very pleasing to the Western ear. So going up a full octave sounds very nice, and going up a major fifth sounds very nice. So the overtones are in harmony with the fundamental, and that's why stringed instruments sound so nice. And in fact, what distinguishes a piano from a harpsichord or a violin is how much energy there is in each of the overtones compared to the fundamental. As you move the energy around, you get a different sound, and that corresponds to a different instrument. So this is the theory. I'd sort of like to demonstrate that now. Let me bring up this. Let me explain what you're seeing. So this is showing you how much energy there is in each frequency. So this is already, it's taken that whatever sound there is in the room, and it's converted into frequency. So when I ask the violin to play me an A, you should see a spike at the fundamental and then all the harmonics. Going to ruin it a little bit by talking, but here is the fundamental. What's happening at the top here is a recording, so you can sort of see how it was at different times. So you see, you get the fundamental, and then 2 times, 3 times, 4 times, 5 times, 6 times, all the way up. You get a very nice series of harmonics that are all integer multiples of the fundamental. Now, let's have a go with somebody else. It's not really a string, but should we do the flute? Or let's do the flutes. No, just play your lowest note, I think would be the best. So that's not bad at all. You get quite a nice series, you can see it better up here, of, again, integer multiples of the fundamental. Even though it's a wind instrument, it's very similar to the string mathematically. So here's the fundamental, and then you get this, the 2 times, 3 times, 4 times. 4 is a bit stronger than the others. Shall we see what the oboe does? Again, you see a nice series of harmonics. It's not exactly what I was expecting for this. Okay, we'll come back to that a little bit later. So I showed you the first 3 on the previous slide, but this series goes on forever. There are infinitely many harmonics. Each one is just evenly spaced, so each one you get another multiple of the fundamental. And I've just shown you the first 8 here, and in the red dots, that's where the harmonic would be, so those are the multiples of the frequency, and the green dot shows you the nearest key on the piano. So in an equal tempered scale, where would the nearest note be? And the reason I wanted to show you this, just a little aside, is that you see there's a little bit of a mismatch here on number 7, that the 7th harmonic is not very close to any of the notes on an equal tempered scale. And so that would sound a little bit discordant if you had too much of the 7th harmonic. And so the hammers on a piano will hit the string a 7th of the way down so that they don't excite the 7th harmonic, so that the piano sounds nicer. So they take advantage of that in the positioning of the hammers deliberately to avoid any 7th harmonic. Okay, so back to the question. So there's quite a lot of information in all these harmonics, and one nice way to present it is through this staircase function. So what I'm showing here is on the bottom is frequency, and I just count how many harmonics are there below that frequency. So every time I cross a harmonic, I go up by a step. So I get the fundamental, and then when I hit the 2nd and the 3rd and the 4th, I just go up a step, and I'm just counting. And so because they're so equally spaced, you get this very nice regular staircase function. So the question, can you hear the length of a string, says if I tell you what all these frequencies are, so I tell you what this staircase function is, can you tell me how long the string is? And the answer is yes. Well, so there's a number that you need to know, which depends on what the string is made of and how thick it is and what the tension in the string is. On the violin, there are 4 strings. They're all roughly the same length, but they sound very different. That's because they're different thicknesses. And you change the tension, that's how you tune the instrument. So, but assuming I know all that, if I have the same string, can I tell you how long it is from the note that it makes? And the answer is yes. There's just an inverse relationship. The shorter the string, the higher the frequency, the higher the note. And essentially, that's how stringed instruments work. You put your finger on the string to decide which note you want to make. And so if I hear a note, or in particular if a musician heard a note from a string, they could tell exactly where the finger must have been placed, and therefore how long the string has to be. So this answer, can you hear the length of the string? The answer is yes, and it's just one frequency is enough, the fundamental. So what about drums? What happens with drums? So here I've shown you the vibration, the mathematical idealization of the vibration of a circular drum, which I've just bashed mathematically somewhere. And again, you see it's quite a complicated motion that the membrane of the drum is doing. But again, you can break it down into these simpler motions, which are oscillating at fixed frequencies. So there's a fundamental mode that's just going up and down in the middle, and then there are various more complicated, in this case, higher harmonics. So the staircase function in this case looks something like this. It's not so regular as it is for a string because the frequencies of the harmonics are not so nicely related for a drum as they are for a stringed instrument. And the question is, if I give you the staircase function, assuming I know the material properties, the tension, and how thick the membrane is, can you tell me what the shape of the drum is? Because if I change the shape, then I change the staircase function. So if I give you the staircase function, can you tell me the shape? And even when he wrote his paper in 66, Katz already knew that the staircase function was enough to tell you what the area of the drum was, and it was enough to tell you what the circumference was. So it certainly tells you some things about the shape. So I've got a little example here. So I've done two drums. There's an oval drum and a square drum. And I'm showing you the harmonics in the middle. So the red lines are the harmonics of the oval, and the dots, the black dots, are the harmonics of the square. So if I just had this distinguish between these two drums, then it would be enough, because obviously even the fundamental is different between these two. That would be enough to distinguish them. But if I increase the size of the square, then I can lower all the frequencies, and eventually I get to a point where the fundamental matches for these two drums. But I could still tell them apart by looking at the second harmonic. But if I allow the square to be a rectangle and change the aspect ratio, I could arrange it so that the second harmonic matches as well. But I could still tell them apart by looking at the third harmonic. But if I round the corners a little bit, then I could get the third harmonic to match. Now, the fourth harmonic, etc., they're still different. But the question is, if I made it so that all the harmonics had to match all the way up to infinity, would the drum necessarily have to be an oval? Would it have to be exactly the same shape? You can see that it's already starting to look a little bit like this one, and all I did was match the first three. So it seems plausible that given all the staircase function of all the harmonics, you would in fact determine the whole shape of the drum. But in fact, in 1992, a group of mathematicians called Gordon, Webb, and Walt came up with a counterexample. So there were two drums that had different shapes, but they had exactly the same staircase function, exactly the same set of harmonics. And these are the drums that they came up with. So you can tell that this is a mathematical theory, right? So each of these drums is made up by 7 triangles, just arranged in a slightly different order. So how do you go about proving that these have exactly the same harmonics? So you could mathematically beat one of these drums, which means I go and calculate exactly what the frequencies are. So for a string, I can do that, and for a square drum, I could do it. But for these drums, they're so complicated that I can't do it exactly. I'd have to get a computer to do it, and I'd have to do it approximately. And that means there's inevitably some numerical error, some round-off error or whatever when the computer does it. So I couldn't be sure that I hadn't missed a very small difference between two of the harmonics. In particular, there are also infinitely many harmonics, so it would take a long time to check infinitely many numbers. So the way you show that these two vibrate at the very same frequencies, that you do a technique called transplantation. So you take an oscillation on one of the drums, and you use it, you map it to the other drum and show that for every oscillation on this drum, there must be a corresponding oscillation on the other one at exactly the same frequency. And in fact, you need 3 copies of the oscillation on the left to get the oscillation on the right. And I like to think of it in terms of paper folding, so this is how it sort of works. So you imagine taking the oscillation on the left, you take 3 copies of it, you fold it over, and you transplant it to the right. And if you add up all those 3 things that you get on the right, you find it works, that it matches very smoothly, and you get an oscillation on the right. So that's how the proof works. What's interesting about this is the triangle is sort of irrelevant in that proof. What's important is the fact that it's 7 copies of the same shape that are made by continually reflecting over the edges. And what that means is if you fold it all up as though you were making a paper dolly, so you fold them up and you put them on top of each other, and then you cut out a shape. When you unfold them, then exactly the same proof will work. And so you have 2 drums again that have exactly the same set of harmonics, even though they're different. Now, the question now arises, so what is determined by the staircase function? And you can see these two, they almost look like chemical molecules. They look like different isomers of the same chemical. And so there are lots of things they have in common. They each have a pointy bit. They have two sticky in bits here. They've got 3 times there are 2 legs coming out. They've both got 2 rectangular holes. There are lots of things in common, but they've just got it arranged in slightly different places. So this problem has analogues in other branches of physics, in particular in quantum mechanics and blackbody radiation and things like that. And in those cases, it really is these high harmonics, the whole staircase function, that's important. But for real drums, it's really the low harmonics that are important. So just, I've basically finished, but just as a little coda, I want to go back to this question of the fact that the eigenvalues, the harmonics for a circular drum, are not in this nice, pleasant ratio of generating octaves and fifths. So this is the theoretical calculation of the harmonics for a circular drum. And if this drum was tuned to A2, then the second harmonic would actually be F3 instead of E, so it would be a sixth. And then the third harmonic would actually be A sharp, which would be quite discordant, I think, with the A. So for some drums, this is all right. For a bass drum, you don't really want it to be tuned. You want it to have a wide range of frequencies so you can play in any key effectively. But drums like kettle drums are tuned to a certain frequency, to a certain note. So why do kettle drums sound so nice, given this theory says that they should not? And the answer is all the things that this very simple mathematical theory misses out. And in particular for drums, the air resistance is very important. That changes the eigenvalues. So both the kettle and the fact that you're having to displace the air. And the result of that is that it dampens out some of these modes and it shifts the others a little bit so that they're almost in this nice ratio. So in particular, the fundamental gets damped out, and the one you hear mainly is the second harmonic. And the ones that are left are almost in this nice ratio. But they're sort of in multiples of a missing fundamental here. So there's a fundamental which is missing, but if it was there, then it would have more or less the same as the eigenvalues of the string. And now if Adrian's kindly brought his kettle drums in, even though he was not playing today, so we can just test that theory.
Okay.
Go for it. Yes, it is at 0. Here we're seeing the second, third, fourth, fifth, sixth, and there's the missing first here. You can sort of see that the fundamental is missing. And so that means that if you touch a string when you play it, you kill the fundamental and it jumps an octave because you get to the second harmonic. But if you touch the drum in the middle when you play it, it makes absolutely no difference because the fundamental has already been damped out. The knock-on effect is if you hit the drum in the middle, you're trying to excite the fundamental, but that's not the key mode. And so it sounds awful because it's damped out. Very good. I think, should we stop that?
Thank you.